Hi, I'm Jenny. I'm an engineering manager here at Oculus, and I lead a team that works on forward-looking input for both software and hardware. So we think a lot about how people will interact in the future. And later on, you'll meet Jonathan Ravaz, a designer and prototyper who I work very closely with. We, along with many others, have been on this kind of epic journey working on hand input and interaction. We've spent years working on this stuff. And it's not very often we get to show you what goes on inside the company, but we're incredibly excited to share some of it here with you today and hopefully get all of you excited to build experiences with hands. Here's a quick overview. First, we'll talk about input's relationship to content and what adding a new input means for our ecosystem. Then exploring new territory with a new technology like hand tracking. Designing hand input for our target platform, Quest. Creating building blocks to make it easy. And finally, optimizing our interactions for human variability. And throughout, we'll talk about lessons we learned that you can hopefully apply to your content. If you look at input historically in both VR and in general computing, we can see that improvements in input are tightly coupled to step function changes in both content quality and types of content. New input enables new experiences, and new experiences can require new input. But everything you can build on a platform is limited by the way that people interact. Input defines the boundaries of the content universe. And when a new input like hands is added, input expands and the content universe expands with it. And in our Oculus products, we've already seen several step function improvements in both content quality and variety related to input evolution. But the most dramatic jump was in our PC platform. We started off with the primary input being a gaming controller, which didn't really let us move beyond seated experiences. But 3 years ago, we released the touch controllers, which brought the magic of hand controllers into VR. And while the hardware of the touch controllers was being developed, we internally built dozens of experiences to understand their value and kind of build out this map of an unknown experience space. And that was just the tip of the iceberg compared to what you all did when touch came out. And the touch controllers are a great combination of a hand and a tool together. They feel like a super-powered extension of the hand. And the hardware was designed to tightly couple physical hand controls with virtual hand actions, and hands have been incredibly important in VR ever since. Many people remember the first time they experienced social presence in VR through the magic of touch. It's kind of a magical moment. But what happens when we have the ability to decouple our hands from devices? We get hand tracking. Breakthroughs in computer vision technology have finally allowed hand tracking to become feasible in our products. And this unlocks the possibility of a more natural input method and potentially a new step function in content. And technologies like hand tracking create possibility, but technology is not enough. We really need to build experiences to illustrate their value. And this is a hard problem. Hands are a new input paradigm, but the rewards are huge. Think about all the things you can do with your hands in the real world. You can grasp and manipulate fine tools. You can sense temperature, like hot and cold, and textures. And hands also greatly enhance social communication. And we certainly can't do all of those things in VR yet, but hand input is a super approachable and low-friction input, and it requires no additional hardware. It can easily be the first input you use when you put on a headset, and it's a foundational technology that crosses all of spatial computing, including augmented reality. Hands can also serve as a connective tissue to other devices in the future that let you use the right tool for the right job in the right context. And we really want to build towards a future ecosystem where we can unlock more and more use cases. Finally, self and social presence get a lot more interesting with fully articulated hands. We've heard from many developers that people want hands that are sized more like their own, and with hand tracking, a virtual hand can become more fitted and authentic to you. But designing interaction for hands is much more open than designing for a device. Hands can do practically unlimited numbers of things, but our goal was to find the highest value interactions that can be performed confidently by a user and execute their needs. Over the years, we started off very, very broad, and then we narrowed into a few interaction primitives, just like a mouse or a touchscreen has. instead of trying to replicate everything your hand can do in the real world, because that's almost infinite. But before we know enough to create interaction primitives, we really have to survey the space to understand the capabilities of hands in VR. So when we begin working with a new input technology like hands, we really don't know what they can do yet, and so we build a lot of prototypes to chart a map. And when we're prototyping, we're trying to understand the ways in which the things we're testing are good and bad in different scenarios. And the knowledge that we build is this kind of sparse qualitative map of a new experience space. And with hand tracking, one of the first sparse maps we built was exploring hand representation and how it feels to have a fully articulated hand. So we built a lot of hands to understand the space, using some assets you might recognize from previous games. And we also created many new ones. We looked at a wide range of realistic to abstract and organic to rigid elements, and we actually learned a lot. We learned that hand representation sets usage expectations, and the more realistic the hand, the more realistic the expectations. And this is especially true when you can fully articulate your hand. And we also learned that our minds adapt pretty well to hand proxies, but non-human hands start to feel a little bit more tool-like than a human hand. We also looked at realistic hands. This is a cleaned up texture and hand scan done by a technical artist of his own hand. But realistic hands are difficult to make and expensive to produce, and they take a lot of steps to clean up. And they also set really high expectations of interaction realism. And as it turns out, there is an uncanny valley for hands. You can start with the texture, but that's not really enough. Hands have tendons and muscles and hairs, and the list just goes on. And aiming for realism also means dealing with a lot of deformation issues and sets limitations on movements and skinning. But we also made hairy hands. And we made a lot of hands in VR using Quill, like this witch-like hand. And tons of creature hands with goo and moss and other organic elements, like the ones you see here. Played with non-human hands using the Farlands hands. And we even put hands on hands on hands. And we built a circle of dancing hands just because we could. And we could have spent forever working on hand representation to maximize our learnings, but we learned a lot from just a few. And when we're prototyping, we really want our ideas to be different enough to provide good coverage of the space. We don't want to end up at a local maximum and miss a global maximum. So as we worked more with hands, we started to ask ourselves, what should it feel like the moment a user first sees their hands in VR? And then how do we gracefully handle tracking issues such as occlusion or tracking volume limitations? So here's a simple alpha fade. Here's a simple particle effect to kind of convey a feeling of magic when you first see your hands. Here we tried to communicate the feeling of your hands materializing. And here we took that effect further and made it kind of a shatter. Here's an example of showing an explicit tracking volume rather than having it be implied. And here's our favorite, a radial alpha effect that's simple, responsive, and elegant. But the total amount of prototyping we do also varies with the scope of the technology we're working with. And hand tracking, just like the touch controllers, is a foundational input technology and has taken a lot of prototyping to map, as in years. But as we narrow the scope of the idea space we're working in from everything you can possibly do to a cluster of ideas like object manipulation, and finally down to a single interaction like selection, the amount of prototyping we do decreases. And when we started moving into using hands as input, it became critical to break down the problem into simple interaction primitives. So we began by sampling the interaction space to look at a spectrum of simple primitives all the way to dexterous manipulation. And one of the first things we looked at was using direct touch to poke buttons and sliders. Here's a simple pinch interaction to spawn and throw a ping pong ball. Here we can use the ability to fully articulate our fingers to push small blocks around and arrange them. And we also have a more complicated grab engine to do dexterous manipulation of objects such as these. And one of the big things we learned is that the complexity and the quality of the interaction scales with the quality of the tracking technology. This grab engine works incredibly well with the amazing internal technology we have from Facebook Reality Labs, but not so well with inside-out tracking or mobile compute. Let's recap some of our takeaways so far. Hand representation sets usage expectations, although fractal hands don't exactly lead to an exponential increase in productivity. Our minds adapt pretty well to hand proxies. Hands have an uncanny valley. Interaction quality scales with technology quality. And interaction primitives are necessary. Unlike controllers, our hands don't come with buttons and triggers and analog sticks. We have to invent a new language for those. But through all of these prototypes and experiences we built out this great knowledge map in the beginning of a new experience space, but we were doing it in a very unconstrained way using internal technologies that are much higher fidelity than a platform we can actually ship on. And now Jonathan's going to talk to you about how we design hand input for our target platform, Quest.
Thank you, Jenny. Hi, everyone. My team and myself have been working on making hand input a reality for the Oculus Quest. Hand input is just as much of a design problem as it is for machine learning or computer vision or engineering. Today, I will be walking you through some of our learnings, giving you an insight into our design process, and sharing the design principles we have developed along the way. Let's start by establishing the major design challenges our team had to face in making hands a new input modality. Firstly, existing behaviors. Every person is an expert in using their own hands. Individual expectations are extremely high for what hand tracking should enable. There is also a strong bias from people's past experience of using other input devices such as touchscreens, keyboards, and computer mice. There's a strong cultural influence from science fiction, movies, or video games that give people the preconceptions of what hand tracking should feel like and look like and behave like. Fictional user interfaces are designed to look cool and complex, but what we require from a real-life input method is simplicity and functionality. Whilst inside-out hand tracking provides high-fidelity hand presence for virtually zero effort, it has physical constraints that limit its ability to completely fulfill one's expectations. Some of these constraints are inherent limitations of camera-based tracking, such as occlusion, the tracking volume, or the lack of haptic feedback. All three of these challenges were providing useful guidance for our team when thinking about hand input. These challenges will be equally important for you when you will be designing hand-driven experiences. In order to elevate hands to the capabilities of other input devices, such as our touch controllers, they need to be able to perform the following three interaction primitives: targeting, selection, and manipulation. These core elements enable experiences to have compelling and rich interactions that can solely rely on hand input. Compelling interactions are easy and fun to perform. They are mindful about our ergonomic properties. One of the main targets for our team was to develop mid-air interaction models that afford long, repetitive usage while also minimizing muscle strain. Awkward posture refers to a position of the body that is different from its default neutral position when performing tasks. When you are in an awkward position, muscles operate less efficiently, and you use more force to complete a simple task. A neutral posture is a body position that causes the least amount of stress and strain for your muscles, joints, or ligaments. An ideal neutral posture for hand interactions is when your arm is close to your body and the elbow is lined up with your hip. This allows for a person to stay in this position for extended periods of time, and also it provides a comfortable field of view for the tracking cameras over the hands. Being mindful about the ergonomic properties of the body is, in general, great practice when we are designing spatial experiences. This becomes even more important in cases when we are using hands as a direct input mechanism, such as pushing virtual buttons with our fingertips. The work envelope is a guiding principle for understanding the ergonomic cost of certain distances from the body. This concept can also be applied as a tool for organizing information in space based on the frequency of the reaches of the user. The work envelope identifies three main zones: the primary, secondary, and tertiary zones. It is important to be mindful about the ergonomic properties of the human body, but consider these as features rather than limitations. Just as the human body has its own constraints to consider, so does computer vision. Computer vision-based hand tracking can provide a frictionless, amazing user experience. However, as with all camera-based technologies, there are some inherent limitations that need to be addressed in the design process. Two of the major considerations are the following: being mindful about the tracking volume of the headset, and maintaining the line of sight between the camera and the subject of tracking. To help illustrate this, I will walk you through a case study of a hand-based menu design, one of our first explorations. Our initial designs for this concept revolved around a watch-like menu design. This involved interactions that require both of your hands. The early prototypes seemed really promising, but we really had a blind spot as a design team. We were well aware of the inside-out tracking limitations, and when we were testing these prototypes, we were performing the interactions with avoidance in mind. Once we had put the prototypes through our usability study, it became quickly evident that participants had a hard time understanding what computer vision can and cannot provide. Participants expected hand tracking to just work in all conditions, and these high expectations had to be met by our design choices. Based on the learnings of the study, we have made some adjustments. We came up with an interaction that allowed the people to perform the actions with a single hand, avoiding the overlap of two hands. These changes were a double win. They addressed the computer vision problem, but they also resulted in a more accessible solution. The adjustments led to a significant improvement in the reliability and efficiency of the component. Prototyping early, testing early, and not making presumptions without testing them in real situations are key to a successful design process when working with hand input. So far, we have talked about the ergonomic properties and hardware considerations. Now let's talk about what hands actually enable in terms of interactions. Raycasting and other various casting methods have a proven track record of being an adequate selection technique for further than hands-rich interactions in VR or gaming. However, when using bare hands as input, natural hand tremor and tracking issues can interfere with the casting accuracy and precision. These inaccuracies became amplified when driving the casting with smaller muscle groups, such as your fingertips or wrist. In order to address this problem, new strategies had to be identified for stabilizing the casting of the hands. The most successful solution we have found was using a secondary position on the body to anchor the race vector. While position A dictates its origin, position B sets its direction. This combination of two positions results in a more stable and precise casting experience. The particular position chosen for the origin and direction points greatly influences the speed, precision, and ergonomic cost of the casting. Different combinations are suitable for different regions in space. Based on our tracking capabilities, we have evaluated 4 feasible options for the origin and 3 feasible options for the directional points. The origin points are calculated using an inverse kinematic, or for short, IK model. Whilst IK can be inaccurate at times, this doesn't affect the selection precision thanks to the filtering applied. In this video, you can see some of our early prototypes that we have used for evaluation in our usability study. All of the origin and control point combinations had their benefits and limitations. We found a way to combine the best of these techniques into a single model, which addressed many of their ergonomic and accuracy concerns. This model is mixing the user's gaze direction into the equation. fluidly switching between various origin points. We call this the dynamic model. Casting-based selection can be enhanced by additional interaction techniques in order to further increase precision and to provide methods for multi-object selection. In this example, we use drawing to enable group selection and to make targeting more robust. When interacting in 3 dimensions, we find that using 2 hands not only improves efficiency, but can also help to make spatial input more comprehensible to the user. This quote from Hinckley is just as relevant today as it was back in 1994. The frame, trombone, and hook are 3 selection technique concepts, all leveraging this bimanual model, each addressing problems such as selection of occluded objects or group selection. Another powerful technique to enhance the capabilities of hands is remapping them. Hand mapping is a method for indirect selection that translates the hand movements from the body space to the target space. Like moving a mouse on a table and driving a cursor on the screen, mapping enables more ergonomic and precise interactions that are independent of the distance between the body and the target. Mapping the hand's movement is particularly effective when paired with restrictions of the degrees of freedom of the interaction. This is something we often experience in our physical reality when opening cupboards or turning keys or pulling on levers. Locking interactions to specific axes creates interactions that are both accurate and, most importantly, satisfying. In this keyboard prototype, we are remapping the user's 3-dimensional input, 3-dimensional hand motion, onto a 2D surface, making the interaction way more robust. The ratio between the surface and the hand, as well as the gain of the hand movement, is fine-tuned to increase the speed and accuracy of typing. Adjusting the ratio and gain based on the context of the interface has a great effect on precision and ergonomic cost of the action. Developing a robust manipulation solution for hand input is a difficult design challenge due to the natural inaccuracies of the human hands and limitations of computer vision. Remapping your hand to accommodate these limitations can be a super effective tool to overcome these difficulties. In 3D space, objects can be translated, rotated, and scaled along 3 axes. Combining these grants a total of 9 possible degrees of freedom. Rather than providing all 9 degrees of freedom at all times to manipulate, we believe that there is a consistent hierarchy in spatial manipulation tasks for the vast majority of typical situations. Our working assumption is that simultaneous XYZ translation is the primary task, followed by Y rotation and uniform scaling as secondary tasks. In this prototype, we are using a mapped indirect manipulation method to move, rotate, and scale the object. Mapping is a great tool for increasing precision, reducing complexity, and reducing ergonomic strain. Most of the things we have talked about so far were about the underlying mechanics of these interactions and what people could do with them. Or in other words, what these new interactions really afford. However, these new abstract affordances don't teach you how to use them or what to actually do with them. People can be guided to perform these unfamiliar interactions by foreshadowing functionality and providing feedback, in other words, signifying the affordances. The 3 main frontiers that can address the lack of familiarity of hand interactions are self-haptic feedback, visual signifiers, and audio signifiers. One of the most challenging aspects of bare hand input is the lack of discrete states. Pressing a floating virtual button only using hand tracking, despite all the effort put into visual and audio signifiers, can result in a slightly inconsistent user experience. To address this concern, we started to explore gestures that can provide natural, self-haptic feedback, such as pinching or tapping one's other hand. Pinching is a powerful gesture for enabling a broad range of possibilities for hands as an input modality. It is relatively easy to track using computer vision, has a discrete down and up state, It is limited to a certain range of motion, and most importantly, provides self-haptic feedback. As one of the first explorations around the potential of pinch, we have developed a series of direct interface components that were founded on the idea of pinch and pull components. This gesture and component combination allows people to operate switches, pickers, sliders, lists with confidence. The pinch and pull components provide 4 major benefits against the traditional push method. It is a binary action. You are exactly aware when the interaction is starting and when it ends. There is no clipping. The interaction is translated between the interface and the user's body. Save some space. Creating interfaces for indirect interactions can be space-consuming. Pinch and pull components allow because of their condensed state, they allow for more compact interfaces. And it most importantly follows expectations. Unlike in the case of a push button, there is no expectation for haptic feedback when releasing an elastic object. Whilst the affordances, signifiers, and hands are all collocated in the case of pinch and pull interactions, this is not necessarily the case with indirect, far-field interaction models, such as our system on the Oculus Quest. In these cases, the constant guidance and feedback from signifiers is necessity for compelling, robust interactions. As an example, we wanted to show you the anatomy of a casting-based interaction model. The hand representation provides a platform for communicating tracking confidence as well as pinch feedback. In this prototype, the outline of the hand is used to reinforce pinching. The beam is a signifier near the pinch position. It tells the user the direction of their cast. It invites the user to squeeze with the thumb and index finger, again, reinforcing the pinch-based interaction. And the cursor is placed at the end of the raycast, away from you. The representation of the cursor is constantly driven by the pinch distance between the 2 fingers. It doesn't just provide pinch feedback, but it informs the user whether their hands are being tracked or not. Now let's look at all these components working together in harmony. The indirect interaction model in this prototype is utilizing the dynamic casting model, the beam, the cursor, and the hand representation signifiers to create a compelling user experience that can be completely seamlessly integrated on top of our existing platform. Now I will give the word back to Jenny to discuss how we created these building blocks for scalability. Thank you.
Thanks, Jonathan. When we began our journey, we built a lot of bespoke prototypes to build out the experience map. But as we gained conviction and started targeting our interactions towards our shipping product, starting from scratch every single time wasn't scalable. So here's how we created building blocks for a scalable, flexible, rapid prototyping in the form of an interaction toolkit. When we're exploring input, there's many permutations of hardware sensors and interactions to try, and a toolkit allows us to efficiently survey the space by doing 2 things. One is that we can quickly plug in new input devices or modalities, or use them in tandem to explore multimodal input. The second is that we can experiment with many different interactions before down selection, like the ones Jonathan showed. And the nature of a toolkit lets us not commit to one idea, but instead allows us to experiment and consolidate designs into a common system of components. And then when we gain conviction, we can create an opinionated interaction framework like a product snapshot and use engineering to harden the interactions with heuristics and algorithms to make it feel reliable and responsive. And this is exactly what we did for hand input in the core UX for Quest. And because we're working with multiple inputs, it's critical to have a clean architecture to abstract them such that adding a new input modality doesn't add complexity. So what we really want is input plus component scaling instead of input times component scaling. So basically, we want all of our components to deal with this abstracted layer rather than modifying every component every time we add a new input. And this concept of abstraction is very similar to an abstract syntax tree used by a compiler, and it drastically speeds up our prototyping. We built a lot of compelling concepts before we built a toolkit, but we didn't really build them on a robust foundation, and we kind of paid for it later on. Here's an example of how we abstract a button component. For any component, we abstract everything away into something we call a manipulator so that it works across a variety of input and interaction. And in this case, a button will respond to the indirect raycasting that Jonathan showed, or a direct touch with a fingertip, or a pinch, all through a manipulator. And here's an example scene built on our interaction toolkit where we can easily try out all of the different indirect raycasting combinations. And we can do so with either a hand or a controller or any other input that we want to use. And this lets us really rapidly experiment with combinations and settings to gain conviction and test different interactions across different input modalities. So here's some of our learnings. If you're building interfaces, we really recommend that you build components that abstract input to allow scalable experimentation and compatibility. And the second is that we recommend you build abstractions sooner rather than later to reduce complexity and tech debt when you're working with hands and controllers. And the last thing we want to talk to you about today is how we optimize designing our interactions for human variability to make them feel reliable and responsive across a diverse user base. And to really understand the variability between human beings, user research is an indispensable tool. We wouldn't need it if there wasn't any variability between humans. Otherwise, I could sit in a room and design something that works perfectly for myself, and by extension, all of you. But I'm not you, and you're not me, and our hardware is ergonomically designed to fit a large range of variability of human heads and hands, and our input really needs to meet those same standards. And designing high-value interactions is one piece, but making them feel great across the population is another challenge. And to account for human variability, we use user research for three things. The first is to understand user intent and observe how users react to a new technology. One of the reasons that people who build products often get surprised by the way people use them is that because they've spent all this time making it. And when you work on a product, you've got the curse of knowledge, and you can't really get rid of it. The second is to compare it to other input methods. We do a lot of testing on input effectiveness to look at throughput and accuracy and other variables. And lastly, we use user research to do data collection to optimize for performance and threshold tuning. And I'm going to focus a little bit on that last one, which is how we optimize for performance using the example of pressing a button in 3 dimensions. People bring a lot of expectations from the real world when they use hands as input, and a lot of people expect it to work like a touchscreen device does. But this presents many design challenges like the lack of haptic feedback that Jonathan mentioned, latency, occlusion, human hand size variability, and depth cues. Pressing a button is a simple concept, but it's not simple to do in 3 dimensions. And when we're trying to optimize an interaction, we break it apart into different variables so that we can create something more polished in the future. And we use user research to understand and test and figure out which variables are correlated and which have no effect. And this helps create the boundaries of the design space. And Jonathan talked a lot about affordances and signifiers earlier, which are critical for hands as input. And for a 3D button, we really wanted to understand what types of affordances had what effects. So we built a lot of them, which we have a few examples here. And so we explored visual shape, collision shape, continuous lateral information, continuous z-depth information, and we looked at how these affordances affected performance across a diverse set of users. And for a button, one of the critical things to understand is what button size gives us the best performance, in addition to considering ergonomics and reach. We do a lot of classical human-computer interaction testing, and Fitt's law predicts the timing relationship between distance to the target to the width of the target. So here we have a Fitt's ring, and we're testing and understanding the timing it takes to hit a button at a particular size. We're also looking at accuracy and misses and other relationships between variables. And we're looking for the point at which performance evens out, and we reach diminishing returns as a button grows larger or smaller. The video here is a recording of a previous test done with very, very small button sizes. So when we're analyzing performance, we record a lot of data so we can go back in time and try to classify errors, and we also look at velocity and trajectory. So the lines that you see in this image are the path of the person's finger in space when performing a fits test. The width indicates the velocity their finger is moving, and the flow of the line is the path direction. And that weird spike you see is just a tracking error. But as we're building interfaces, we also want to understand how dense we can build them, such that we can reduce misses and accidental activations of other elements, given a particular gutter size, button size, and shape. And the precision of an input really determines how dense we can build our interfaces. The size of a finger drives the density of a 2D touchscreen interface, but other properties beyond that govern the density of a 3D touch interface, such as trajectory and latency and jitter. And here we're running the same type of test as I showed earlier for buttons, but this time we're specifically using the indirect raycasting model we designed for Quest. And all of the targets are set at the primary distance our user interface is designed to be at. And the nice thing is that we can use the same series of tests across different interaction models. Here is a density test using targets that are the smallest possible size, and this is taken directly from the Quest system UX. And again, this lets us tease out properties of human motion and efficiency of our input without distracting the user with a polished home environment, so everything you see is gray box. These are just some of the many examples of how we use user research to dial in performance and make interactions feel great. And to summarize, design guidelines are necessary for direct and indirect manipulation to really optimize for human variability. And we will be publishing our guidelines at a later date for you to use. And we've already done a lot of work to create these guidelines, so please use them when you build interfaces and other content. And let's recap what we've learned today. We started off talking about input's relationship to content and how a new input affects our ecosystem. Exploring new territory with new technologies like hand tracking. Designing hand input for our target platform, Quest. Creating building blocks like an interaction toolkit to make it easy. And finally, optimizing our interactions for human variability. And we've kind of spent the last few years exploring new territory and making hand interaction usable for you. And this stuff is super hard. It's a new paradigm. And we've done a lot of research, but we really don't know everything. And we're going to equip you with tools, but you're going to have to do the work too. But we can't wait to see the amazing things you create when hand tracking is released to inspire us. And if you want to learn more about the technology, please watch Rob Wang's talk tomorrow, where he's going to do a deep dive on the computer vision.
Yeah, and if you have any questions to us, please join us after the talk in the speaker pavilion at the end of the corridor. We will be there to answer your questions. Thank you.
Thank you.